In earlier lectures, we concluded that there is an internal electric field present inside the depletion region which is responsible for drift current, which is further responsible for maintaining equilibrium in the depletion region. We assume that the electric field is zero in the neutral regions outside the depletion region. Thus, there should be a constant potential, say Vn, in the neutral N region and a constant potential Vp in the neutral P region and a potential difference V0 equal to Vn minus Vp. This potential difference V0 is given various names like built-in potential, potential barrier and contact potential. However, all these mean the same thing. This contact potential appearing across the depletion region is a built-in potential barrier as it is necessary for the maintenance of equilibrium at the junction. It does not imply any external potential. Indeed, it cannot be measured by placing a voltmeter across the semiconductor device because new contact potentials are formed at each probe, cancelling the contact potential V0. We have actually three equations. The first equation is this: diffusion current density plus drift current density is 0. This means that the net current density in the depletion region is 0. The other two equations are these two equations means that the drift current density plus the diffusion current density due to either charge carriers is 0, which means there is no net buildup of either type of charge carriers at either side of the depletion region. In this lecture, we will try to find a relationship between contact potential V0 and doping concentration on each side of the junction. For that, we can use either of the equation, third equation or the second equation. But I will use the second equation, which is the drift current density due to holes plus diffusion current density due to holes is 0. Drift current density is given by. Similarly, diffusion current density due to holes is given by. After cancelling the charge q, we have also we know electric field is equal to negative of potential gradient. We can rearrange this equation like this. By using Einstein relation, we can write mobility divided by diffusion constant of hole to be equal to charge divided by kT. Now, integrating the equation, we will get Vn and Vp represents the potential in the N-type and P-type region. Similarly, P suffix P represents the whole concentration in P-type region and Pn represents the whole concentration in N-type region. After integrating, you will get we already know that Vn minus Vp is equal to contact potential V0. Therefore, we have formula for contact potential to be equal to kTyq into natural logarithm of whole concentration in P-type region divided by whole concentration in N-type region. If we apply the mass action law and convert the whole concentration into electron concentration, then we will get another formula for contact potential which is equal to kTyq into natural logarithm of free electron concentration in N-type region divided by free electron concentration in P-type region. Assuming a general non-degenerately doped semiconductor in which the whole concentration in the P-type region is approximately equal to acceptor impurity concentration and free electron concentration in N-type region is approximately equal to Donor concentration. We have the formula for contact potential like this. By mass action law, we can write hole concentration in the n-type region to be approximately equal to square of intrinsic carrier concentration divided by free electron concentration in the n-type region, which is equal to square of intrinsic carrier concentration divided by doping concentration. Substituting the values of hole concentration in the p-type region to be equal to Na and concentration of hole in the n-type region to be equal to Ni square divided by Nd. We will get another formula for contact potential, which is equal to kTyq into natural logarithm of Na into Nd divided by square of intrinsic carrier concentration.